So this first talk of the conference, solving a multi-step language processing task with large language models. It's already in the name. We're talking about large language models. And first, I want to talk about expectations regarding large language models. So sometimes people really expect the most from these new tools, since they are somehow related to AGI, artificial general intelligence, or basically developed trying to get there. The consensus is that currently large language models are not AGI. I don't want to burden my talk defining where we have reached some general intelligence and where not, because this would require probably somewhat more expertise in this field. However, since large language models haven't quite gotten there, but they are quite powerful, we want to talk about what these tools offer, because they are very powerful tools and they offer new ways of solving problems, and equally they replace previous solutions. So for example, in information extraction, whereas previously we would have trained a new model on an information extraction task, now we resort to using large language models as an alternative. So, what's new? This image is quite famous. It's from the original Transformers paper. Attention is all you need. And you can see here the general architecture. And what's interesting is that large language models basically have stuck to this architecture. So there are some technical adaptations. For example, the training procedure is different. We have the positional embedding has evolved quite a lot. There have been many suggestions. The current state of the art is rotary position embeddings and several new forms of basically building from these transformer blocks the entire architecture. For example, having a mixture of experts where you have several linear layers which are at every run basically chosen flexibly. Also, of course, they are called large language models, right? So they are very big and increasingly bigger because that's basically where people have found emerging effects that really are so enticing. Common sizes for large language models are 7 billion, 13 billion for the smallest ones, and then going up to 70 billion and much, much more. Number of parameters, yeah. So what happened when you get bigger and bigger is you have emergent effects where there's really coherent text generation possible. So you feed in some context and you generate some text based on this context with really a coherence that really makes you think, are we, what's possible? Because it's so convincing. And these context lengths that you can put in also get bigger and bigger. Now we're already at 1 million tokens that you can feed in. That's almost the entirety of the work of Shakespeare. And also, next to being coherent, there are some benchmark tests where people compare their large language models against each other. And in terms of logic, reasoning, and general language understanding, they just get better and better. And also connected to a size, like the bigger, the better they tend to perform in these benchmarks. However, also there's a trend towards reducing the size for better usability, because the bigger they are, the less usable also. And then also a crucial point is that you can fine-tune your large language model to behave like a chatbot. So this is this basic ChatGPT-like mode that probably everybody is familiar here, where you have a user input and you get an answer. And this also enables problem solutions where you basically define your problem in natural language and then ask your large language model to solve this problem. And this also ties into the field of prompt engineering, which you might have heard of. Right, so how does this text generation work? I will give a very short example. Consider the sentence, the quite famous pangram for the English language, so it contains every letter of the alphabet. The quick brown fox jumps over the lazy. And so what's missing here is dog. And so first, we tokenize the sentence. Here, since the words are very short, basically each word corresponds to a token. And then we give this to the large language model. And what this basically is, as a generative model, is something that defines the conditional probability for the next token given these this sequence of input tokens. And I've done this for a quite recent model, Llama 3, the 8 billion parameter version. And you can see that basically, as we expect, dog is by far the most likely next token. And everything else has orders of magnitude less probability. So, and this is basically why is this? Because in the training process, we repeatedly show this sentence because it's a very famous sentence, and you basically scrape the internet and give it to the model, and so it sees this over and over again, and so it's much more likely to predict in the end this sentence over any other continuation. So with these basically probabilities, what's missing is then you have some clever ways of choosing the next token, and there are parameters like temperature, the number of tokens, this top K, which you want to consider, or the maximum probability, or the smallest set of next tokens, which is which adds up to some maximum probability, which you define, which is top P. But to keep it short, there are different strategies to get this next token. Also, you can choose to always take the most likely one. That's called greedy. But you can to have more variance. You can sample, or you could use beam search, which takes the joint probabilities of a couple of next tokens and then chooses the most likely one. So how would, under the hood, when you use something like a chatbot and you type something in and you get an answer, how would this work? First, the prompt is something that is the text that you give to the large language model in order to generate some new text. In certain examples, you might want to feed in some data from a database, for example. And then you ask, with this data from the database, answer this user query, for example. You feed it into the large language model, and you get your answer. However, it doesn't need to stop there. You can iterate through this process a couple of times using tools, for example, like chain of thought, also literally tools like function calling. If you have some planning modules or memory involved, you could take it a step further and produce something like an agent. However, all these things might happen between what you type in and what you get back. And then the use case for this is, for example, you want to have a report generated or a summarization. So basically a one shot, one user input and one output. Or the more famous use case, you have a chat, which you then always prepend the history of the previous of the conversation, and then ask for a completion or a generation. Let me give you a quick introduction into how the data retrieval step and adding information from a database works. Very quickly, you have a document, and there are many ways to solve this, but usually very simply, you split it up and you use a so-called embedding model to generate a vector, 728 or more numbers, and you put it into the vector in a vector database. Then once you have a user query, you search for semantic similarity between the user query and all the chunks in your database, and then you select with some clever mechanism the best fitting chunks and add them to the prompt as text. Just like you say, here's some context, please answer the following question which the user asked from this context. And this sort of mode of generating an answer based on data from a database is called retrieval augmented generation, quite fittingly, in my opinion. And let me give you an example where this, is quite useful. In any scenario where you want to sort of not rely on some knowledge stored in the weights of your large language model, but you just want to rely on that the model basically is able to understand the entire context that you give it and answers the question that you have based on this context. This is useful, and as an example for a quite new president in Argentina, end of last year, you would ask who is the current president of Argentina, and then ask Mixtral. Here is a model from Mistral AI, and the answer is I don't know, basically, because my knowledge is cut off here, and so it can't possibly know the answer. What you can do is you can in an automated way feed a list of presidents from Argentina, add it to the prompt, and then get your answer, which is correct, namely that currently it's Javier Milei. I've mentioned previously that the context lengths get larger and larger. And then you might ask, why would you use this retrieval augmented generation if you can just put all your information in this large context? The answer is that for now, retrieval augmented generation still has a better performance. And this is something that people, for example, test with this needle in a haystack test. So you place in your context length, which is here for ChatGPT-4, 128,000 tokens, and you can put in. And you place your sum fact on the top, somewhere between the bottom of this prompt and the top, and you ask GPT-4 basically to give you the answer that you put in there somewhere. Basically, give me the needle that I put in this haystack. And you can see that the longer the context gets, the less, the lower the accuracy of your of your answer, basically. And so, and you see this for other models as well. And the conclusion is basically that if you can get away with a smaller context and put the right information there, leaving out a lot of other context, you will get a better result. Also, if you get an answer then, and you use retrieval augmented generation, what you can do is you can use natural language inference, which basically checks, is the input in agreement to my output, in order to verify if the language model has given you the correct answer. Which basically also helps you avoid this big problem that people have where large language models just hallucinate. So they give you confidently an answer which is wrong, factually. Also, it's costly. So having 1 million tokens as a context is well, produces some latency, as well as, of course, it just costs time on your hardware, since the attention mechanism in the large language model scales quadratically with the sequence length. All right. Let me go back to my clock so I don't lose it. All right. Another thing that I mentioned is large language models can use tools. What does that mean? Do they go somewhere and try out something for themselves and then get back to you with the answer? No. What basically is possible is that if you have a process with several steps, basically several prompts and outputs that you further process, you can have predefined code executions, like you define a function yourself in normal code, and you can describe to the large language model what this function does and how to use it, and then basically it helps you determine how to call this function and with what parameters. An example for this would, for example, would be you can check the weather, like what temperature it's currently. Like you have a function which just uses a weather API or so, or you use a calculator and so on. You could also do this, of course, in a less predefined way, let's say. Like you could you have your answer, and then in this answer you use some regex, like, okay, this is the argument that I would like a value for. You extract the value, and then you call the function with a little more effort. But since people since companies that train large language models have sort of analyzed that this is a valid sort of use case, they have trained models to be able to give you a function call back, basically. So how does it work in detail? Again, you have a function in code. You need to define what this function, what the name of this function, describe it, like checks the weather. And you have to define the arguments, like the names for the arguments, the types, the description, and whether it's necessary or not, or if there's a default. And then you give this basically function description in addition to your user query to the large language model, and it can then decide to call a function in order to answer this question, and gives you back basically the name of the function to call and a list of arguments and their respective values, which are extracted from the user query or somehow a result of the processing that happens internally. Oops. And with this information, you can then call the function yourself, get the output, and then feed it back for the next step in your process. All right. With this, we've basically reached the end of the general description, and now I would like to go a little bit more into detail of how you would actually set up or solve a process that I described. Like, it is a general task, and it can be split up in several subtasks. Let's first define what could like this vague process that I'm talking about, what's part of this. So in general, you could have some case-specific user data, like a message or some scanned documents that you have in an information extraction process. In addition, you might want to add some rules that or guidelines that describe the process. Like you could also hard bake this into your into how you structure the code for your process. But you could also have just a document defining if some threshold is reached, and this threshold I give a number to this in my documents, some X, then Y happens, and then this is defined in some process describing document. Additionally, you might want to have access to up-to-date information like web searches or the weather forecast. And then, of course, you want your process solution. Like, example, I would like to know the weather for New York. The answer is the weather is currently it's 11 degrees Celsius and it's raining. All right. And the question is, how do you put all this together? Let me give you a more concrete example based on this. So let's say we are a train company, and a customer wants compensation for a delayed train. So first of all, what you would need, of course, is a database of train journeys, including the times where the train left and arrived, in order for you to check whether there was actually a delay or not. Then, of course, a customer would have some claim, and they would maybe they would have you could have a predefined document which a customer might have to fill in their data. You could also have a chatbot, for example, and we will look at this later, where you get a message in text where the customer is free to describe their problem. Maybe they will say that they are angry, whatsoever. In any case, there will be some customer inquiry or message. And then you, of course, have to define if the customer wants a compensation, when do you pay a compensation? Because at some point you will, but not for everything. So there will be, legally, there will be passenger rights defined, cancellation policies, and the amount of compensation. And then in the end, let's make the use case that we have a customer support which gets this message and then gets an automated response for the customer. And this response then should be directed to the customer. It should mention if this request is eligible, and maybe also list the reason for the train delay and the compensation amount if possible. And so that would be a concrete example of how all these different steps might play together. All right. We had before this big bubble of how do you bring this together, and since now the title of the slide is multistep, we will basically compartmentalize this problem into several different steps. And the idea is basically to have something that's a self-contained language problem using this retrieval augmented generation. Basically, you pull together all the information for solving a certain step in your process, and then you ask the language model to give you an answer for this sub-step. And importantly, there's no additional knowledge required because you've pulled together all the required information. And in the following schematics, basically, I will define this arrow here defines how information flows, basically text either from some documents or a previous step in your multi-step process. So you start somewhere. Basically, maybe you get a message from your customer. Next step might be you read in this message. You check some norms, basically telling you how to solve the process, what steps come first. And then this can be iterated, and basically several individual self-contained sub-steps will be chained together until you reach, in the end, your solution. What's good about solving this problem in this manner is, first of all, if you use an LLM, you have to care less and less about the structure of your text. Like it's extremely useful for customer messages, for example, because you might imagine there are many different formats in which someone might write a text. So it might be very sloppily, just very short sentences, but giving the necessary information. Or someone might have a really elaborate speech and in the end not give you what you need. Also, with the latest sort of line of large language models, we don't need fine-tuning or training. It is possible if you have certain steps along the way, for example, an information extraction step where you need a better performance, and a general large language model is not capable of doing it as robustly as you would like. And also, these models are pretty interchangeable. So sometimes you might want to fine-tune it, sometimes you might want to wait for 2 months until the next model is out there and try it with that one. Because you have sort of defined some parameters which are important and maybe legally relevant in process-defining documents, which are read in by the large language model, you can add more criteria for example, a compensation, or you change the amount of compensation like from 10% to 25%. And you can do this easily in your documents without having to fiddle around with your code. And also you can easily expand on your problem because you have independent steps. You can just add a step here or put something in between. And since it's already structured separately, this is very straightforward to do. All right. Now I would like to show you basically a live demo of how the customer support for the train company could have been solved, as an example. And first I would like to basically give you a schematic of how it's built. So we have a customer message. For example, hi, I'm Lorraine and my train is delayed. Help me. So first, I would classify the intent. So, and why that's relevant is because I would like to have several different solutions or routes basically in my customer support chatbot. So one maybe for a compensation request, and the other one will be a lost item request. If I sort of find out that it's about a compensation, first of all, I would have to actually check, is this eligible? Like, first I would have to find out what train are we talking about? So from this free text, I need some data relevant to actually finding the train connection that is being talked about here. And so we need a train database, but we need to extract the information from the free text and match it to the train database to find the train. Then there are some passenger rights that define for this number of minutes of delay. This is the compensation that you will get. And this will be stored in an external document. And we determine the eligibility from the information of the train and this passenger rights document. And then we generate a response. It's directed to the customer, and the customer support can basically look at it, maybe change a word or two, and then send it out. The other option, as I already mentioned, would be retrieve matching items. And here also we have a database of this train company where there will be images of, okay, we found this backpack, then you describe what backpack it is. And with this database, you again match whether the customer query sort of matches to any item in the database, and then you generate a response with the result. Okay, and with this, we actually get there to the live demo, which is always fun to have a live demo because everything might happen. But right. Oh, I'm on the wrong side of the... All right. So here it is. Can you see it? Yeah. We have a customer support chatbot. This is basically connected to an LLM. In this case, it's Mixtral, which I already mentioned before. And well, let's just first say hi. What happens in the beginning is always when a message comes in, you first classify the intent. Since hi is neither a compensation request nor a lost item request, this is other, and it will just fall back to normal chat. Okay, then let's start. I have a couple of examples. First message from Marie, in this case. We give some information on when it was retrieved. So last Thursday, the 5th of September, well, it's in the future, my train between Hamburg and Cologne was delayed by 139 minutes. The train was supposed to arrive at 7:36. I missed my connection to Paris and had to wait 2 hours for the next train. I would like to know if I can get a refund for the delay. Pretty straightforward. So first, as you can see, this is now a compensation request. The intent is pretty clear. The user is asking for compensation for a delayed train. Next step, we extract information relevant for the train journey. You can see that it has found that the arrival date time was scheduled to be the 5th of September at 7:36. It was meant to leave. It left from Hamburg and went to Cologne. And so looking at the database, of course, I've chosen a message which corresponds to an item in my fake database. But we have retrieved the right train. Then checking, is it eligible for compensation? And here, I just fed in basically from Deutsche Bahn this document, your passenger rights. Could be anything, of course. You can define this yourself. And every time it determines an eligibility, the large language model, it sees this entire document, all these things that are relevant. And of course, for this example, it's relevant how many minutes of delay did the train experience. So in this case, we are at, let me check, 139 minutes, which is, first of all, eligible in any case. And the amount is 50% of the price paid for the single ticket because it's more than 120 minutes. And then in the end, you get basically your message ready to be sent out, directed towards Marie. Thank you for contacting us and for your patience. Listing basically, well, you have this 50% of your paid price, and then also mentioning that this is not enough, basically information, and you would need to give the details of the ticket in order to proceed. All right, let me give you maybe, looking at the time, one or two more examples. So what happens if we don't specify enough information to actually find out what train we're talking about? Then we can, for example, abort here and say, well, this is not enough. I don't know. I can't match a train for this. And then what might be interesting also, and maybe we take this as the last one, here it's quite hard, quite a hard task. So the message was received on the 6th of August, and then the customer says, I want a refund. Yesterday my train was supposed to arrive in Cologne at 5 p.m. and 6 minutes. I think it was probably already late when it left in Hamburg. Can you help me? So there are several quite hard information extraction tasks here. First of all, yesterday basically gives you when the train was supposed to arrive, and then you have to match the date when the message was received with basically the time which the customer mentioned. And then second step, this is also, I guess, I mean, it's not super hard, but it also doesn't list 17:06 as a time. And so again, we have a compensation request, and amazingly, because I prepared this, of course, and I checked whether it's working, the large language model has correctly found the day before, basically, and has turned 5 p.m. and 6 minutes to 17:06. And we find the train, it has a signal disruption, but here it's not eligible because and I also, of course, chose it for this reason, it's only 59 minutes, and that's not 60. And so, dear customer, thank you for contacting us. We understand the inconvenience, blah, blah, blah. But it's not 60 minutes, and so unfortunately you don't get a refund. Okay, this is basically what I wanted to show you for this first route of customer support chatbot. The other one is, and it's not as involved, it's just, imagine you have this database of lost items, so things are left in a train, and then the use case would be they arrive somewhere in a train company office or so, and then the people working there take a picture, write a small description, say it's located, for example, in Berlin or Cologne or whatever, and you can, of course, extend this. There's a lot of possibilities involved here. And what you could, for example, do is, well, as a user, you're, say, I lost my Jansport backpack. It is turquoise. Can you help me with that? And so being customer support, this message then gets through. You see, all right, this matches quite well to the description. You can have a look at this image. Let's say maybe this person gets to your office, then you would have it in front of your screen and describe it. And the person needs to describe it to you, which is a normal procedure for getting a lost item back. And then also, if it's not in front of you in the office as a customer support, you would have this this message detailing what that we have found this backpack. It matches your description where it is, namely in Duisburg here, and that you could retrieve it. And if you contact us. So that's basically it that I wanted to show you. And with that, I hope there are some questions. I look forward to them, and would open up the round. Thank you for your attention.
All right. Yes. So thank you very much, Fabian, for the very interesting presentation and also the demo. I believe we have some mics in the back.
Can you show us the code for this? So for the prompt and the intent classification stuff, because I wonder if it's really just like prompts and hoping it works, or if there more.
I can show you the code. It's not. I didn't prepare it, but it's mainly that. So you have an app, which by the way, this uses Streamlit. Which is quite easy to set up. So don't give me much credit for the UI. And then there's a compensation request line of basically going down and lost item. And all the different steps I've chosen to just make a function out of. And well, there are some pre-processing and some post-processing. But in the end, basically all these different functions, different steps correspond to, in the center of it, a call to the large language model using the previously extracted information, using the user query, and some instruction on how to answer this. Yeah, is there anything in particular you're interested in? Or? Okay.
Because I was impressed that it found the scheduled arrival time based on the we've just providing yesterday. Did you do something with the prompt to guide the model, or was this just working out of the box?
No, this all uses the same. But I don't know if I will find it. But it in the end, here is what I define for the model. So these are the fields that I would like to have extracted. And it lists here date and time of train departure, for example, format, this. So day, month, year. So 08 of 09/2024, hour and minute. And it's just the way that it can map from the message received on and yesterday to the actual departure time. And I want to mention that this will not always work. There are things where you're really surprised, and sometimes you're surprised how doesn't this work? It's so straightforward, it's so simple. You can see it here. I'm looking at the prompt, it's right there. Please tell me the answer. And so you sometimes really have to make more and more railways, sort of to make this single steps more robust, which is part of the process. You split your problem apart, and then you make each step more and more robust until it works with high confidence.
Can you hear me, or should I keep on looking? Yes, so I have a question, because in the beginning of your presentation, you showed us this chart that shows that basically the longer the context, the more difficult for the LLM it is to, exactly this one. That's basically the performance drops if the valuable information is in a very big context and it's like in the wrong place. But then in the example with the Deutsche Bahn, I noticed that as a context for like whether the person can be eligible for the refund, you take the entire page full of information that is probably mostly not relevant to the question. So I wonder if you considered chunking this text and having like an additional step where you actually select the context more accurately.
Yeah, that's a really good question. And well, the strategy is try it out in the easy way, and then if it doesn't work, you have to basically get more simple and simple in your requests. And also, yes, I've taken the entire passenger rights, but they are also, well, there are maybe several thousands of tokens. And as a reference, this mixed rule that I'm using has 32,000 tokens context length, and so it's good enough that it gets it. And then exactly as you said, if it doesn't work and actually while playing around with it, I realized that this step is actually it would be better to chunk this, because it's actually a lot and the answers are not as reliable as I would have wanted. But that's the strategy, exactly what you say.
All right, let's have maybe one more question, and then we unfortunately have to end it. But I'm sure that if you have more questions, Fabian will talk to you afterwards happily.
Yeah, thanks for the great presentation. Also for the demo. It's great. The flexibility of LLMs and so on is great. And I was just wondering, so this is in line with the last question. Suddenly I think, is it working?
I think so, yeah.
It's better. So how do you make sure that it actually works? Because you have so many components, right, in your pipeline. Mm-hmm. So now it doesn't work again. So you haven't talked really about measuring accuracy, measuring errors, measuring robustness and so on. Yeah, so how do you evaluate this? Have you done anything there? Any interesting insights?
So for this demo, not, but let's because it doesn't save the intermediate outcomes here. What the strategy would be to basically go from a free text answer to what you can see here. Basically, what happens is I try to get a JSON back with predefined keys and predefined value placeholders, basically. And so what I would do is I would have a test set of messages, and then I would say for this message, basically the outcome that I want is eligible, true. Delay reason, other. Compensation, I would have to fine tune this a little bit, or basically extract that it should be the 50%, and then this delay I do not with an LLM. But anyways, I would list some outcomes that I want for a single message after this entire process, and then I could basically very easily get the accuracy. I also mentioned this natural language inference check, which is something that's a little bit more involved. You use a BERT model, for example, and you say, is the answer in agreement with my context? And that would be something that I would use if it was a free text output. But for this demo, I haven't done it. Excuse me?
I mean, it's just curious, right? So, how easy would it be to produce a false answer, or?
Easy, I guess. You, of course, again, this is the process. You start simple, you see it doesn't work. You have to make it more robust. You might make the single problems easier, and until you reach a point where you say, this is it works for the next 10 prompts that I'm showing in this demo, and then that's good enough for me. If you have a production model, of course, you would go this extra step in checking really carefully and testing basically adversarial attacks or something like this, prompt engineering wise, to make it answer something wrong. And that would be the strategy.